Hi friends, welcome to my channel Born to Learn. Today we are going to learn about factors affecting the resistance of a conductor and resistivity. Factors affecting the resistance of a conductor. The electrical resistance of a conductor or a wire depends on the following factors. 1. Length of a conductor. 2. Area of cross section of the conductor or thickness of the conductor. 3. Nature of the material of the conductor. And 4. Temperature of the conductor. We will now describe how the resistance depends on these factors. 1. Effect of length of the conductor. It has been found by the experiments that on increasing the length of the wire, its resistance increases, and on the decreasing of the length of the wire, its resistance decreases. Actually, the resistance of a conductor is directly proportional to its length. That is, resistance inversely proportional to length, where L is the length of the conductor. Since the resistance of a wire is directly proportional to its length, therefore, when the length of a wire is doubled, its resistance also gets doubled. And if the length of a wire is halved, then its resistance also gets halved. When we double the length of a wire, then this can be considered to be equivalent to two resistance joined in series, and the resultant resistance is the sum of the two resistances, which is double the original value. From this discussion, we conclude that a long wire or long conductor has more resistance and a short wire has less resistance. Second one, effect of area of cross section of the conductor. It has been found by experiments that the resistance of the conductor is inversely proportional to its area of cross section, that is, resistance inversely proportional 1 by A, where A is area of cross section of conductor. Since the resistance of wire or conductor is inversely proportional to its area of cross section, therefore, when the area of cross section of a wire is doubled, its resistance gets halved. And if the area of cross section of wire is halved, then its resistance will get doubled. We know that a thick wire has a greater area of cross section, whereas a thin wire has a smaller area of cross section. This means that a thick wire has less resistance and a thin wire has more resistance. A thick wire having large area of cross section can be considered equivalent to a large number of thin wires connected in parallel. And we know that if we have two resistance wires connected in parallel, their resultant resistance is halved. So, doubling the area of cross section of a wire will therefore halve the resistance. From the above discussion, it is clear that to make resistance wires or resistors, 1. Short length of a thick wire is used for getting low resistance, and 2. Long length of a thin wire is used for getting high resistance. The thickness of a wire is usually represented by its diameter. It can be shown by calculations that the resistance of a wire is inversely proportional to the square of its diameter. Thus, when the diameter of a wire is doubled, made 2 times, its resistance becomes 1/4, and if the diameter of the wire is halved, made 1 by 2, then its resistance becomes 4 times. Similarly, if the diameter of a wire is tripled, made 3 times, then its resistance will become 1 by 3 whole square, or 1 by 9th of its original value. Third one, effect of the nature of material of the conductor. The electrical resistance of a conductor, say a wire, depends on the nature of the material of which it is made. Some materials have low resistance, whereas others have high resistance. For example, if we take two similar wires having equal lengths and diameters of copper metal and nichrome alloy, we will find that the resistance of nichrome wire is about 60 times more than that of the copper wire. This shows that the resistance of a conductor depends on the nature of the material of the conductor. Fourth one, effect of temperature. It has been found that the resistance of all pure metals increasing on the rising the temperature and decreasing on lowering the temperature. But the resistance of alloys like manganese, tungsten and nichrome is almost unaffected by temperature. Resistivity. It has been found by experiments that 1. The resistance of a given conductor is directly proportional to its length, that is, R proportional to L. 2. The resistance of a given conductor is inversely proportional to its area of cross section, that is, R inversely proportional to 1 by A. By combining the relations 1 and 2, we get R inversely proportional by L by A, R equal to P into L by A, where P rho is a constant known as resistivity of the material of the conductor. Resistivity is also known as specific resistance. From equation 3, it is clear that for a given conductor having a specified length L and an area of cross section A, the resistance R is directly proportional to its resistivity P. So, if we change the material of a conductor to one whose resistivity is 2 times, then the resistance will also become 2 times. And if we change the material of a conductor to one whose resistivity is 3 times, then the resistance will also become 3 times. If we rearrange equation 3, we can write it as resistivity rho equal to R into A by L, where R equal to resistance of the conductor, A equal to area of cross section of the conductor, and L equal to length of the conductor. This formula for calculating the resistivity of the material of a conductor should be memorized because it will be used to solve numerical problems by using this formula. We will now obtain the definition of resistivity. Let us take a conductor having a unit area of cross section of 1 meter square and a length of 1 meter. So putting A equal to 1 and L equal to 1 in the equation 4, we get resistivity rho equal to R. Thus the resistivity of a substance is numerically equal to the resistance of a rod of that substance, which is 1 meter long and 1 square meter in cross section. Since the length of Y is 1 meter and the area of cross section is 1 square meter, so it becomes a 1 meter cube. So we can also say that the resistivity of a substance is equal to the resistance between the opposite faces of a 1 meter cube of the substance. We will now find out the unit of resistivity. We have just seen that resistivity rho equal to R into A by L. Now to get the unit of resistivity rho, we should put the unit of resistivity or area of cross section A and length L in the above equation. We know that the unit of resistance R is ohm. The unit of area section of cross section A is meter square and the unit of length is meter. So putting these units in the above equation, we get unit of resistivity rho equal to ohm into meter square by meter equal to ohm meter. Thus the SI unit of resistivity is ohm meter, which is written in the symbol as ohms meter. Please note that the resistivity of a substance does not depend on its length or thickness. It depends on the nature of the substance and temperature. The resistivity of a substance is its characteristics property. So we can use the resistivity values to compare the resistance of two or more substances. Another point to be noted is that just as when we talk of resistance in the context of electricity, it actually means electricity resistance. In the same way, when we talk of resistivity, it actually means electrical resistivity. The resistivity of copper is 1.69 into 10 to the power of minus 8 ohm meter. We mean that if we take a rod of copper metal 1 meter long and 1 square meter in area of cross section, then its resistance will be 1.69 into 10 to the power of minus 8 ohms. Please note that a good conductor of electricity should have a low resistivity and a poor conductor of electricity will have a high resistivity. From the above table, we find that all the metals silver has lowest resistivity of 1.60 into 10 to the power of minus ohm meter. The resistivities of alloys are much more higher than those of all pure metals from which they are made. For example, the resistivity of manganese, which is an alloy of copper, manganese, and nickel is about 25 times more than that of copper, and the resistivity of tungsten, which is an alloy of copper and nickel, is about 30 times more than that of copper metal. It is due to their high resistivities that manganese and tungsten alloys are used to make resistance wires or resistors used in electronic appliances to reduce the current in an electrical circuit. Another alloy having a high resistivity is nichrome. This is an alloy of nickel, chromium, manganese and iron having a resistivity of about 60 times more than that of copper. The heating elements or heating coils of electrical heating appliances such as electrical iron and toaster etc. are made of an alloy rather than a pure metal because the resistivity of an alloy is much higher than that of pure metal, and an alloy does not undergo oxidation or burn easily even at high temperature when it is red hot. For example, nichrome alloy is used for making the heating elements for of electrical appliances such as electric iron, toaster, electric kettle, room heaters, water heaters, geysers, and hair dryers, etc. because nichrome has very high resistivity due to which heating element made of nichrome has a high resistance and produces a lot of heat on passing current. 2. Nichrome does not undergo oxidation or burn easily even at high temperature. Due to this, nichrome wire can be kept red hot without burning or breaking in air. The resistivity of conductors like metals is very low. The resistivity of the most of the metals increases with temperature. On the other hand, the resistivity of insulators like ebonite, glass and diamond is very high and does not change with temperature. The resistivity of semiconductors like silicon and germanium is in between those of conductors and insulators and decreases on increasing the temperature. Semiconductors are proving to be of great practical importance because of their marked change in conducting properties with temperature, impurity, concentration, etc. Semiconductors are used for making solar cells and transistors